morning students. In today's class we will discuss how to calculate the fault current for the given power system network. So I'll read out the question. A 50 Hz 50 MVA 13.2 kilovolt generator with star grounded is connected to a line through a delta star transformer as shown in the figure. So this is the given power system network consisting of a generator with star point solidly grounded, and the positive, negative and zero sequence reactances are given, followed by a transformer, then a transmission line. Okay, so they had given point P is the point of fault, and the transformer rating is also given. The reactances of the transformer is also given, and the transmission line is section QR whose reactances are given. Okay, so note down that power system is not having any load at the terminal point. Okay, so this power system network is ending at point R, which is left open. So it is an unloaded power system network. So we are asked to calculate the fault current for LG fault, LL fault and LLG fault. So as we have discussed in the previous class, I told you the 3 steps for estimating the unsymmetrical fault current. Okay, so the first step is to draw the positive, negative, zero sequence network of the given power system separately. Step 2, we have to draw the Thevenin equivalent positive sequence network, Thevenin equivalent negative sequence network and Thevenin equivalent zero sequence network. And only the Thevenin equivalent positive sequence network will have VPF and equivalent positive sequence impedance. Okay, the negative and zero sequence networks, Thevenin's networks, will not have the pre-fault voltage VPF. And step 3, depending upon the type of fault, these 3 equivalent circuits should be connected accordingly. Okay, so now let us take the generator ratings as the base values. Okay, and they had not, for the transmission line, they had not given the actual values. So no need to calculate the new values. So take the given reactances as such. Consider the given reactances as such for drawing the sequence networks. Okay. So for the given power system network, we draw the positive sequence network like this. So generator has internal EMF EA in series with the positive sequence impedance of the generator J.1. Then we have the transformer, positive sequence reactance is written J.1. Then we have the transmission line whose positive sequence reactance is written J.03. And the terminal R is open, and we have marked the fault point P. Okay. See, now for this you have to calculate the equivalent impedance at the fault point. So fault point is point P. Okay. So how to calculate the Thevenin's equivalent impedance? We have to remove the voltage source. We have to short the voltage source, and this side it will be left free. So when calculating the equivalent impedance, this J.1 and J.03 is redundant reactances. Okay, so this will not be of any value. So the equivalent impedance at the fault point P is nothing but J.1. Okay, so we are not considering this J.1 and J.03 because on the right hand side of fault point P, the terminal is left open. Okay, so these 2 reactances are redundant elements. So we are not considering those 2 reactances in calculating the Thevenin equivalent impedance. So Thevenin equivalent impedance at fault point Z1 equivalent is J.1. In the same way, draw the negative sequence network. So negative sequence network is similar to positive sequence network, except for we removed the EMF EA. Okay, so X2 of the generator, X2 of the transformer and X2 of the transmission line are written. from the data given in the problem. Okay. Then we write the Thevenin equivalent impedance at the fault point P. Okay. So to the right hand side of the fault point, we have open terminals. So these two elements J.1 and J.03 are redundant. So equivalent impedance at the fault point is J.1. Then we draw the zero sequence network. This is for the generator. X0 of generator is given as J.05. This is the fault point. J.1 is the X0 of transformer. Delta star transformer. So since the primary side of the transformer is delta connected, the series switch on that side is open and the shunt switch is closed. And the secondary side of the transformer is star with neutral solid grounding. So we close the series switch. Okay. Then followed by the transmission line whose X0 zero sequence impedance is J.09. Okay. So now write down the equivalent impedance at fault point. So equivalent, see to the right of the fault point it's open. It's open here as well as here also it's open. So the equivalent impedance is nothing but J.05. Okay. So step 1 is done. So we have drawn the positive, negative and zero sequence networks of the given power system and we have written the impedances and we have calculated the Thevenin equivalent impedance. So after calculating Thevenin's equivalent impedance of the three sequence networks, what we are doing is we are drawing the Thevenin equivalent sequence networks. So this is the Thevenin equivalent positive sequence network which has VPF in series with positive sequence Thevenin equivalent impedance. Okay. And this is the Thevenin's equivalent circuit for the negative sequence network. This is the Thevenin's equivalent zero sequence networks. So now according to step 2, we have drawn the Thevenin equivalent positive sequence, negative sequence and zero sequence network. And this VPF will appear only in the positive sequence network. Okay. And it is an unloaded power system network. At the receiving side, that is terminal R, it is left open. So for an unloaded power system, we consider VPF is equal to 1 per unit. Okay. So now come for the first type of fault, which is LG fault. So for LG fault, we know the three sequence networks will be connected in series. Okay. All the three sequence networks are connected in series. See, this is the Thevenin equivalent positive sequence network. This is the Thevenin equivalent negative sequence network. This is the Thevenin equivalent zero sequence network. So I have connected all the three in series. Okay. So now use the formula which we have derived earlier. For an LG fault without fault impedance, we have IA1 equals IA2 equals IA0 is equal to VPF by Z1 plus Z2 plus Z0. What is Z1, Z2, Z0? They are the Thevenin's equivalent positive sequence, negative sequence and zero sequence impedances. So substitute the values J.1 plus J.1 plus J.05. You will get it as minus J4 per unit. Okay. And for LG fault, the fault current is IF is equal to 3 into IA1, which is 3 into minus J4, which is minus J12 per unit. Okay. So if you want only the magnitude of fault current, it is 12 per unit. The impedances are given in per unit and pre-fault voltage is also taken as 1 per unit. So the value of fault current will be in per unit. To get the fault current in actual units ampere, we need the base current. So we have written the formula for base current. IB is equal to 1000 into MVAB divided by root 3 into KVB. So 1000 into, we have considered the generator rating as the base value. So the MVA rating of the generator divided by root 3 into KVA rating of the KV rating of the generator 13.2. We got it as 2187 amperes. So now to get the magnitude of fault current in the actual units, which is amperes, per unit fault current 12 into the base current 2187. We got it as 26,244 ampere or 26.244 kilo amperes. Okay. So for LG fault, what we have done, we have connected the Thevenin equivalent positive Thevenin equivalent negative and Thevenin equivalent zero sequence network in series. Then we are using the usual formula for finding out the fault current. Okay. So now the second type of fault is double line fault, LL fault. So we know for LL fault, IA0 is equal to 0, VA0 is 0, VA1 is equal to VA2 and IA1 is equal to minus IA2, which implies the combined sequence network of the given power system under LL fault will have positive and negative sequence networks alone connected in parallel. So I have connected the Thevenin equivalent positive network and Thevenin's equivalent negative sequence network in parallel. Okay. And I have written Thevenin's equivalent positive sequence impedance and Thevenin's equivalent negative sequence impedance in the combined network. Understood? So this is the parallel combination of Thevenin's equivalent positive network and Thevenin's equivalent negative sequence network. So now from the derivation you write the formula. So we have IA1 is equal to minus IA2 is equal to VPF divided by Z1 plus Z2. So what is Z1 and Z2? J.1 plus J.1. VPF is 1 per unit. We get IA1 as minus J5 per unit. And for LL fault, the fault current IF is equal to minus J root 3 into IA1, which is minus J root 3 into minus J5. We got it as minus 8.66 per unit. So the magnitude of fault current is 8.66 per unit. To get the fault current in the actual units amperes, we multiply the per unit value by the base value. So we got it as 18,939.42 amperes. Okay. Coming to the third type of fault, it is double line to ground fault. So we already know for a double line to ground fault, IA1 plus IA2 plus IA0 will be equal to 0. VA1 is equal to VA2 is equal to VA3, which implies that all the three sequence networks should be connected in parallel. Okay, so the combined network will have all the three sequence networks connected in parallel. Okay, so we connect the Thevenin's equivalent positive sequence network, Thevenin's equivalent negative sequence network and Thevenin's equivalent zero sequence network in parallel. Okay, and we write down the corresponding values J.1, J.1 and J.05. Okay, so now write down the formula for IA1, which we have derived earlier. So IA1 is equal to VPF divided by Z1 plus Z2 Z0 by Z2 Z0. So on substituting the values of the impedances and on calculating, we will get IA1 is equal to minus J 7.5 per unit. And IA0 is equal to minus IA1 into Z2 by Z2 plus Z0. We get as J5 per unit. Okay. So we calculate IA0 because the fault current for double line to ground fault is 3 into IA0. So IF is equal to 3 IA0, which is 3 into J5, which is J15 per unit. To get the magnitude of fault current, it is only 15 per unit. To get the fault current in amperes, multiply the per unit current by the base value. So we get the fault current as 32,805 amperes. Okay. So as summary, what is the first step? For the given power system, you have to draw the positive sequence, negative sequence and zero sequence network separately. Okay. Step 2, draw the Thevenin's equivalent positive sequence network, Thevenin's equivalent negative sequence network, Thevenin's equivalent zero sequence network. So in Thevenin's equivalent positive sequence network, we have VPF in series with Thevenin's equivalent positive sequence impedance. So this VPF and Thevenin's equivalent positive sequence impedance are calculated with respect to the fault point and the reference. In the same way, calculate the negative sequence Thevenin equivalent impedance and zero sequence Thevenin's equivalent impedance with respect to the fault point. That is very, very important, with respect to the fault point as well as the reference. Okay. Third step is for the given type of fault, connect these three Thevenin equivalent networks accordingly. Okay, so if it is LG fault, all three equivalent networks should be connected in series. If it is LL fault, connect positive and negative sequence in parallel. If it is LLG fault, connect positive, negative and zero sequence Thevenin equivalent impedance networks in parallel.